Now, I start with a new concept that is called sufficiency. In the context of statistical inference, there is a concept which is useful to retain the necessary data without losing any information. What is the literal meaning of the word sufficiency? The literal meaning of the word sufficiency is that it is enough. Sufficient means enough. So, usually we are dealing with the statistical model that we deal in the inference problem is that we say let x 1, x 2, x n be a random sample, meaning thereby that we have data on n observations, or you can say n data points are available to us. Now, in many of the practical problems it becomes difficult to retain the data, because it may occupy a lot of storage space, whether it is on computer or it is in the form of hard copy of the data, and then there is a danger of losing the data. It will be always interesting to say that okay, let us keep the minimum things such that whatever information or whatever useful inferences we want to make, we are not suffering in that. That means, we do not lose any important part of it. A formal specification of this concept is called sufficiency or sufficient statistic in the context of statistical inference. So, let us introduce the formal definition of sufficiency. As before, we have a random sample. So, let x 1, x 2, x n be a random sample from a population, say p theta, theta belonging to say script theta. A statistic. So, a statistic we have already defined. A statistic means a function of observations. So, t, that is t x 1, x 2, x n, which we also write as t x. That means, we are denoting x as x 1, x 2, x n. So, t x is said to be sufficient. Now, what do you mean by sufficient for what? So, we usually mention the word sufficient for the family of probability distributions. In loose terms, we also say sufficient for the parameter theta, meaning thereby that whatever be the parameter under consideration. Many times in the problems we will have one dimensional parameter, two dimensional parameter, etc. In that case, we will have to consider specifically what parameter is being considered. So, the formal definition I am writing for the family of probability distributions, meaning thereby that whatever parameters are under consideration, this could be a scalar or a vector parameter. So, this is said to be sufficient if the conditional distribution of x 1, x 2, x n given t is equal to say small t is independent of theta, of course, except perhaps a null set A, that is on a set A where t takes probability 0. So, this is a exceptional case, but in general the distribution of the random sample given the statistic, if it is independent of the parameter, then we say that this t is independent, then we say that this t is a sufficient statistic. Now, what is the physical interpretation of this definition, that the distribution of x 1, x 2, x n is free from theta, and then we say it is sufficient? What does it mean? It means that now if the distribution is free from theta, that means the distribution of x 1 x 2 x n given t is completely known. So, suppose we know t, we know the distribution of t. Now, this conditional distribution of x 1 x 2 x n given t, since it is free from theta, then that is also known. Therefore, if I merge these two distributions, that is the conditional distribution of x 1 x 2 x n given t and the distribution of t, I get the joint distribution of x 1 x 2 x n and t. From there I get the distribution of x 1 x 2 x n. It means that even if I may not have the initial x 1 x 2 x n with us, but we can generate that distribution once again because of the information, or you can say the distribution of x 1 x 2 x n given t being free from the parameter, and t is known to us. This signifies that if one does not have the original observations x 1 x 2 x n, but has t and a knowledge of the known conditional distribution of x 1 x 2 x n given t, then one can generate say x 1 prime x 2 prime x n prime, which will have the same distribution as x 1 x 2 x n. So, this is called data reduction. As we will show later on that in most of the practical problems, the sufficient statistics will become like one dimensional or two dimensional thing, although you may have any number of observations. So, this data reduction is helpful, and we will show statistically also that basing our decisions on the sufficient statistics is also useful. That means, if there is any inference made in the terms of estimation, testing of hypothesis, etc., if I am making inference based on the sufficient statistics, we are better off. So, let me explain this example, say binomial distribution example. Let me take. Suppose I have x 1 x 2 x n be a random sample from say Bernoulli distribution with parameter p. Here p lies between 0 and 1. Let us consider say t is equal to sigma x I is equal to 1 to n. Let us look at the conditional distribution of, consider the conditional distribution of x 1 x 2 x n given t, that is equal to x 1 is equal to x 1 and so on, x n is equal to x n given t is equal to t, that is equal to probability of x 1 is equal to small x 1 and so on, x n is equal to small x n, t is equal to t divided by probability of t is equal to t. Now, that is equal to, since t is equal to sigma x I, if small x 1 plus small x 2 plus small x n is equal to t, then only this probability will be calculated. In other cases, this will be simply equal to 0. So, that is equal to probability of x 1 is equal to small x 1 and so on, x n minus 1 is equal to small x n minus 1 and x n is equal to t minus sigma x I is equal to 1 to n minus 1 if t is equal to sigma x I is equal to 1 to n, otherwise this is 0. Now, here we can make use of the fact that x 1, x 2, x n are independently distributed Bernoulli random variables. So, if they are independent, this probability of the joint occurrence will be equal to the product of these probabilities. So, this term let me write, this term is anyway 0. So, this term is equal to probability of x 1 is equal to small x 1 and so on, x n minus 1 is equal to small x n minus 1, probability of x n is equal to t minus sigma x I is equal to 1 to n minus 1. That is equal to p to the power x 1 1 minus p to the power 1 minus x 1 and so on, p to the power x n minus 1 1 minus p to the power 1 minus x n minus 1, p to the power t minus sigma x I is equal to 1 to n minus 1, 1 minus p to the power 1 minus t plus sigma x I is equal to 1 to n minus 1 and divided by probability t is equal to t. Now, what is the distribution of t? If x 1, x 2, x n are Bernoullis independent, then this will be binomial n p. So, probability t is equal to t, that will be equal to n c t p to the power t 1 minus p to the power n minus t. Now, we can easily see this terms, this p to the power terms if you add, you will get p to the power t. Similarly, if you add 1 minus p exponents, you will get n minus sigma x I. So, that will cancel out with plus sigma x I, you get n minus t. So, you get it as p to the power t into 1 minus p to the power n minus t divided by n c t p to the power t into 1 minus p to the power n minus t. Now, this term simply cancels out. So, we get it as 1 by n c t. So, this conditional distribution then we can express as probability of x 1 is equal to small x 1 and so on, x n is equal to small x n given t is equal to t, that is equal to 1 by n c t for t is equal to sigma x I and it is equal to 0 if t is not equal to sigma x I. You look at this term, there is no theta, no parameter appearing here, p is not appearing here. So, this is independent of p. So, t is equal to sigma x I is sufficient for the family of Bernoulli distributions we may also say it as that t is sufficient for p here. Now, note here the physical significance of sufficiency. If we are observing x 1, x 2, x n as p independent Bernoulli random variables, that means they are observations related to success or failure in n Bernoullian trials. For example, you are looking at a game of say dart and we are considering hitting a target and we make n aims at the target, then what is important? Whether individual hits, whether this say second one hit correctly, third one did not hit correctly, is it important information, or out of n total attempts how many are correct, that means x, that is sum of xi's. Now, here you see in the concept of sufficiency exactly sigma xi is turning out to be sufficient. Therefore, this is the relevant information, and whatever individual information about x 1, x 2, x n is there, that is not necessary to be retained. In fact, now if we know this and we know the distribution of t, that is binomial n p, we can generate another random sample, let us call it say x 1 prime, x 2 prime, x n prime, which will have Bernoulli 1 p distribution. Let me explain through another example. Say let x 1, x 2, x n be a random sample from Poisson lambda distribution, where lambda is positive. Once again, let us define t is equal to say sigma xi. Now, you can proceed in the same way like in the binomial case. We can consider x 1 is equal to x 1 and so on, x n is equal to x n given t is equal to t. So, arguing as before, we get it as x 1 is equal to x 1 and so on, x n minus 1 is equal to x n minus 1, x n is equal to t minus sigma xi, I is equal to 1 to n minus 1 divided by probability t is equal to t, if t is equal to sigma xi 1 to n, it is equal to 0 if t is not equal to sigma xi 1 to n. So, once again this term will be equal to e to the power minus lambda, lambda to the power x I by x I factorial for I is equal to 1 to n minus 1, and the last one is e to the power minus lambda, lambda to the power t minus sigma xi 1 to n minus 1 divided by t minus sigma xi, I is equal to 1 to n minus 1 factorial. Now, this will become e to the power minus n minus 1 lambda and then e to the power minus n lambda, and also we have in the denominator t. Now, this will follow Poisson n lambda, because Poisson distribution is additive. So, if we are considering a random sample, each one following Poisson lambda, then sigma xi will follow Poisson n lambda. So, we can write e to the power minus n lambda to the power t by t factorial. So, this e to the power minus n lambda cancels out, and if you look at lambda to the power x 1 plus x 2 plus x n minus 1, that cancels here, you get lambda to the power t, and in the denominator also we have lambda to the power t here. So, what we get here? This t factorial will go in the numerator. So, let me write it here. This is equal to t factorial divided by x 1 factorial, x 2 factorial, x n minus 1 factorial, t minus sigma xi, I is equal to 1 to n minus 1 factorial, if t is equal to sigma xi and it is equal to 0, if t is not equal to sigma xi, I is equal to 1 to n. Once again you notice here that this is independent of t. So, t is equal to sigma xi, this is independent of lambda, sorry. So, t is equal to sigma xi is sufficient for the family of Poisson distributions. We may also say that sigma xi is sufficient for the parameter lambda. Now, we can make certain statements here. If I am considering conditional distribution of x1, x2, xn given t, and suppose t is a function of u. Okay. Then if I consider the conditional distribution of x1, x2, xn given u, then that will also be free from the parameter, because if that is not free from the parameter, then the conditional distribution of x1, x2, xn given t will also not be free from the parameter. Therefore, if t is sufficient and t is a function of u, then u is also sufficient. And of course, if I have a one to one function of t, then that will also be sufficient. So, let me give some remarks here. Let t be sufficient for a family of distributions and let t be a function of u, then u is also sufficient for p. Another point that you notice here, that if I consider the conditional distribution of x1, x2, xn given x1 is equal to small x1, x2 is equal to small x2, xn is equal to small xn, then that is always independent of parameter. We can write conditional distribution of say x1 is equal to x1, xn is equal to xn given say x1 is equal to t1 and so on, xn is equal to tn. This is equal to 1 if this t vector is same as x vector, otherwise it is 0. So, this is naturally free from the parameter. Free from the parameter. So, the sample x is always sufficient. So, the full sample is always sufficient. We will be interested in getting some sort of reduction over that. This is known as trivial sufficient statistics. Trivial sufficient statistics. Let me formally prove that given a sufficient statistics, we can generate the original sample. So, let x have distribution say p theta, theta belonging to say script theta, and let t x be sufficient then given t we can generate random variable y which has the same distribution p theta, that is the same distribution of x. So, the conditional distribution of x given t is independent of theta. So, after observing t is equal to t, we conduct a random experiment with outcome say y following the known conditional distribution of x given t, then y and x have the same distribution. Now, another important significance you can say of sufficient statistics is that if we are considering any unbiased estimator, I can have another unbiased estimator which is based on the sufficient statistics, and its variance will be less than or equal to the variance of the initial estimator. This famous result is known as Rao Blackwell Theorem. It is named after the Indian statistician C.R. Rao, who proved this result in 1945, and David Blackwell 1947. Let x1, x2, xn be a random sample from a population with distribution p theta, theta belonging to say script theta. Let delta x be an unbiased estimator of parametric function say g theta, and t be sufficient. Then there exists an unbiased estimator based on t alone, which has variance not more than that of delta x. Now, this is a very significant statement. In a given problem, if I have a sufficient statistics, then I can always base our unbiased estimators on that statistics, so that I will do better than if I do not base it. That means, I will be utilizing the full information in the sample for making my statistical inference. The proof is in fact not very difficult. Let us consider H t to be expectation of delta x given t x is equal to t. Since we know the conditional distribution of x given t is independent of theta, therefore, this expectation is going to be a function of t alone. Okay. This is independent of theta as t is sufficient. So, H t is a statistic, and I can consider it for my estimation purpose. Let us consider expectation of H t. Now, expectation of H t is simply expectation of expectation delta x given t. Now, this is nothing but expectation of delta x, that is equal to g theta. So, this new estimator that I have used H t is unbiased. So, this is unbiased for g theta. Further, let us consider say variance of delta x. Now, this variance of delta x I can express as expectation of variance delta x given t plus variance of expectation delta x given t. Now, this is equal to this quantity, if you see, this is a non-negative quantity, and expectation of delta x given t we have defined to be h t. So, this is equal to variance of h t. So, what we are getting, variance of delta x is equal to variance of h t plus a non-negative quantity, a non-negative quantity. That means, variance of h t is going to be less than or equal to variance of delta x. We will give applications of this result a little later. Another important point that we notice when we are proving that t is equal to sigma x I is sufficient in the two examples that I have considered is that we are already guessing what is a sufficient statistics. Now, in many given problems it may not be obvious that what is sufficient, and therefore, this definition of taking conditional distribution to prove that a given statistic is sufficient may be too cumbersome, and moreover it may give rise to, like we consider conditional distribution of x 1 x 2 x n given say x 1 minus x 2 plus x 3 minus x 4 and so on. It may turn out that this is not free. We may take sigma x I square, it may not be free from theta. Then how to get, or you can say how to guess an sufficient statistic. Fortunately for this, there is a important result called factorization theorem, which readily produces the sufficient statistics. So, this is known as Neyman Fisher factorization theorem. Named after R. A. Fisher and Georgy Neyman, who proved in around 1939. We are not going to give a very rigorous statement and proof of this theorem, which will be applicable to all situations. Rather, we will consider a discrete case here and to write the proof here. For general rigorous statement and proof, see the book of say Lehman and Romano. We are considering a discrete case here. Let x be a discrete random variable with probability mass function say f x theta, theta belonging to script theta. Then T x is sufficient if and only if f x theta is equal to g T x theta into h x for all theta. So, we are calling this as the factorization theorem. What I am saying is the distribution can be written as product of two terms g and h, where h is a term where parameter does not appear. In the term g, the parameter theta appears, but appearance of x is through t alone. So, if that is happening, then we say t is sufficient. So, the factorization means that the part of the distribution where the parameter is involved should involve only the sufficient statistics in the form of variables, and the other term should be free from the parameter. Let us look at a proof of this. So, we are considering the discrete case here. So, let us assume say f x theta is equal to g of T x theta h x. Now, let us consider say probability that T x is equal to t, that is equal to, now this is a probability which is involving a function of the random variable x. So, this can be considered as the sum over the probability mass function over those values of x for which T x is equal to t. If I am assuming this factorization, I can write it as g of T x theta into h x x such that T x is equal to t. Now, in the term h x, this T x is equal to t condition is not it is coming, whereas here T x is equal to t will be true for all the values. So, this term can be taken out of the summation sign. This can be written as g t theta sigma h x over x such that T x is equal to t. So, if I consider probability of x is equal to say x prime given T x is equal to t, that means conditional distribution of x given t, this is equal to 0 if T x prime is not equal to t, and in other case it is equal to probability of x is equal to x prime T x is equal to T x prime divided by probability of T x is equal to t, which is actually equal to T x prime here, because I am taking T x prime is equal to t. So, if you consider this now, probability of x equal to x prime T x equal to T x prime, it is same as probability x equal to x prime. So, this becomes equal to, let me consider only this star portion, let me call this as a star here, I will consider this portion. So, this star portion is equal to p theta x is equal to x prime divided by g t theta sigma h x x such that T x is equal to t, that is equal to g t theta h x prime divided by g t theta h x sigma x such that T x is equal to t. Now, this term cancels out. So, you look at this conditional distribution of x given t. Now, this term is free from the parameter independent of theta. So, the conditional distribution of x given t is independent of the parameter. So, t is sufficient by the definition of the sufficiency. Let us take the converse part of this theorem. Let us assume that t is sufficient for theta. If we assume that t is sufficient for theta, that means I am saying the conditional distribution of x given T x is a function of only x prime and t, that is independent of theta. But this left hand side you can write as p theta x is equal to x prime, T x is equal to T x prime divided by probability T x is equal to T x prime, that is equal to C x prime t if T x prime is equal to t. In other case, of course, it is equal to 0. So, we do not write that case here. This means that probability of x equal to x prime is equal to C x prime t and this term. Now, what is this term? This term will be simply C x prime t g t theta, because I am taking T x prime is equal to t. Now, this is nothing but the factorization, because this term I can write as h x g t theta. So, I have considered this discrete case here, because it is easy to write these conditional probabilities. If the distributions are continuous, then probability of T x equal to t does not make sense, because that will be 0, So, we have to use the conditional density function form. So, the general proof which is given in the Lehman and Romano, this takes care of all these cases. Another point which I would like to mention here, I have taken theta to be a scalar, but suppose theta is a vector here, then what will be the change here? If we make this assumption, this theta will become vector, this theta will become vector here. Here also theta will become a vector, this will become a vector, this will become a vector. So, there is no change in the argument here. That means, if the factorization holds, T will be sufficient. Let us look at the converse part. In the converse part, we are saying that this is free from theta. So, theta will become vector here and it will not make any difference. And here we will write it as a function of t and theta, where theta is a vector parameter. So, this result holds even if theta is a vector parameter. And another thing is about t also. I am writing here t as a one dimensional term, but that is also not must here. T also can have several components, like it could be t 1, t 2, t k. Similarly, theta can be theta 1, theta 2, theta m. So, let me write this as a remark here. The theorem holds if theta and t are vectors. And another point is that their dimensions need not be the same. Their dimensions need not be same. Now, let us revisit our statement. I said that if t is a function of u, then u is also sufficient. Now, in the factorization theorem, if I substitute t as a function of u, then I will be writing it as something like h of u. If I put that thing, then it will mean that u is also sufficient by the same argument. So, let me add that here. If t is sufficient and t is a function, say alpha of u, then let us look at the density function. F of x theta is equal to g of t x theta into h x. This we can write as g of, now t, it is a function of alpha u So, this we can write as g of a function of u. So, we can just alpha u we can write. So, u is also sufficient by factorization theorem. However, if v is a function of t, then v need not be sufficient. If v is a one-to-one function of t, then v is sufficient. Now, this proof is again simple. If we say v is a one-to-one function, say v is equal to beta of t, then we can say t is equal to beta inverse of v. In that case, g t theta you can write as g of beta inverse v theta. That means, it is a function of v and theta. So, v is also sufficient. Now, the definition of sufficiency can be used to prove whether a given statistic is sufficient are not sufficient, because you can find out the conditional distribution of a given statistic and you can see whether it is free from the parameter or not. However, you should know what statistic you are checking, whereas the factorization theorem yields a sufficient statistic because it is appearing there. Now, if we want to prove that something is not a sufficient statistics, then factorization theorem will not be useful, because to show that it cannot be represented is more difficult than saying that it is a function. So, both of the, that is the original definition as well as the factorization theorem, have different uses. Let me give some examples here. So, let x 1, x 2, x n follows a normal distribution with mean mu and variance sigma square. I will consider different cases. As I mentioned to you that the sufficiency is a property of the family of distributions, it is not a property of a variable or a property of the parameter. It is a property which is holding for the family. So, here we are saying mu belongs to R, sigma square is positive. Let us take special cases. Suppose I say sigma square is known, say sigma square is equal to 1. That means, I am saying x 1, x 2, x n follows normal mu 1 distribution. Now, let us write down the joint distribution of x 1, x 2, x n. So, that is equal to product 1 by root 2 pi e to the power minus 1 by 2 x I minus mu square, I is equal to 1 to n. So, this if you see 1 by root 2 pi to the power n e to the power minus sigma 1 by 2 x minus mu square. This we can write as 1 by root 2 pi to the power n e to the power minus sigma x I square by 2 e to the power minus n mu square by 2 plus n mu x bar, because here if I take the cross product term, that is twice mu x I with a minus sign. So, 2 will cancel out, minus minus will become plus. So, we get mu sigma x I, that I write as n mu x bar. Now, if you write this function as h of x and this part we consider as a function of x bar and mu, then it is exactly in the form of factorization theorem. We have one term which is free from the parameter and the other term which is dependent upon the parameter depends on the variable only through x bar. So, by factorization theorem, gives x bar as a sufficient statistic. Now, this family is normal distributions with variances known. So, here the sufficient statistics is x bar. In a rough way we can say x bar is sufficient for mu. Let us take the second case. I take mu is known. If mu is known, say mu is equal to mu naught. In that case, the distribution of x 1, x 2, x n is normal mu naught sigma square. So, the joint distribution of x 1, x 2, x n will become 1 by sigma root 2 pi e to the power minus 1 by 2 x I minus mu naught sigma square, that is equal to 1 by root 2 pi to the power n sigma to the power n e to the power minus. Now, this term we write as sigma x I minus mu naught square by twice sigma square. Here you see I cannot separate out x i's like in the case of sigma known case. So, we can say here that sigma x I, this term I write as say h x, and remaining term I write as g of sigma x I minus mu naught square and sigma square. So, sigma x I minus mu naught square is sufficient for the family of normal distributions. Now, we may do this factorization in different way also. We may write here 1 by root 2 pi to the power n sigma to the power n, and as before let us expand this. So, we get minus sigma x I square by 2 sigma square plus mu n x bar by, so this mu is mu naught here, sigma square and e to the power minus n mu naught square by sigma twice sigma naught square. If you look at this breakup, then I can consider this as a function of x bar and sigma x I square. So, we can also conclude that x bar and sigma x I square is sufficient, which is of course true here. But if you see this one, this is a larger reduction than this, because here the sufficient statistic is 2 dimensional. Here you have sufficient statistic as 1 dimensional, and of course, you can see here that this itself is a function of sigma x I and sigma x I square, because if I expand this I get sigma x I square plus mu naught square minus 2 mu naught x I. So, this is equal to sigma x I square plus n mu naught square minus 2 mu naught sigma x I. So, this is actually a function of this. So, we will prefer this, because this is a higher level of data reduction, because this is 1 dimensional, this is a 2 dimensional. Let us take the case where both mu and sigma square are unknown. Now, notice here, if both are unknown, then I have to consider the joint distribution by treating both mu and sigma square as the parameter. So, this is a 2 dimensional parameter case here, and the product of the individual distributions of x 1, x 2, x n, it is equal to 1 by 2 sigma square x I minus mu square. You expand this, this is equal to 1 by root 2 pi to the power n sigma to the power n e to the power minus n mu square by 2 sigma square minus sigma x I square by twice sigma square plus n mu, or you can say mu sigma x I by sigma square. So, this term you can see it is a function of, this term is a function of sigma x I square and mu and sigma square, and this term you can call h x. So, we conclude that sigma x I square is sufficient. Here you can see that a further reduction is not possible. However, we can consider it in a slightly different way as follows. We may write this as e to the power minus 1 by twice sigma square sigma x I minus x bar whole square minus n by 2 sigma square x bar minus mu square. That means, I have added and subtracted x bar term here. In that case, this is actually sigma x I minus x bar whole square, this is x bar. So, you can conclude that x bar and s square, where we have used earlier the notation s square for 1 by n minus 1 sigma x I minus x bar whole square, that is the sample variance. So, this is sufficient. Now, you see there is no discrepancy in this statement. If I consider x sigma xi and sigma xi square, then this is one to one function of x bar and s square, because from here I can obtain this and from here I can obtain this. So, we can say that when both the parameters in a normal distribution are unknown, then the sample mean and the sample variance are sufficient. Now, many times we are using it as a misnomer that x bar is sufficient for mu and s square is sufficient for sigma square. Actually, we have to say this is sufficient for the family normal mu sigma square, mu belonging to R and sigma square greater than 0. I will just explain this discrepancy may occur if we do not maintain this family here. For example, I take another case, say sigma is equal to sigma square is equal to say sigma is equal to mu, then what happens to the density? It is the distribution is normal mu square. If I have this, then you can look at this breakup here, that joint density, although it is a function of x and mu alone, because sigma has vanished here, this is equal to 1 by root 2 pi to the power n mu to the power n e to the power minus n by 2 minus sigma x I square by twice mu square minus mu sigma x I square by mu square, that is mu. So, here you see this is a function of sigma x I square and mu. Although the parameter is one dimensional, the sufficient statistics is two dimensional. So, although parameter is one dimensional, sigma xi square is sufficient. So, again the statement is again the same, that is sigma xi square is sufficient for this family normal mu square. Of course, we may put mu greater than 0 here. So, sufficiency is a property of the family of distributions. In the next lecture, we will consider few more examples, that is how to apply the factorization theorem to derive the various sufficient statistics, and we will look at the maximal data reduction by means of sufficiency, that is the concept of minimal sufficient statistics. So, in the next lecture we will be considering these concepts.